Many analysts assumed that without a sovereign satellite network like Starlink, Russia's long-range drone fleet would be effectively blinded. They were wrong. Instead of relying on orbit, Russian engineers built a decentralized ghost network that lives entirely in the sky. This is a self-healing web where every drone acts as a relay node. By passing signals node to node across the swarm, the system maintains a constant connection to the operator without ever needing a satellite. These platforms now operate as a living, interactive swarm, capable of sharing data and adjusting their flight paths in real time based on what the lead drones see. To see how much this hardware has changed, we have to look at the original Garand II, also known as the Shahed 136. It was a rigid weapon, a flying engine and a warhead that relied on fixed GPS coordinates, meaning it flew a pre-programmed path it couldn't change. Because those flight paths were so predictable, Ukrainian mobile fire groups were able to park in known corridors and shoot the slow drones down with heavy machine guns. Even if they dodged the bullets, they were defenseless against electronic warfare. Systems like Pokrova spoofed the drones' GPS signals, causing them to drift hundreds of meters off course or crash into empty fields. Without a dense, low-Earth orbit satellite network to manually steer the drones around these obstacles, Russian engineers were forced to build a completely different communication architecture. For more deep dives into the engineering behind modern conflict, make sure you subscribe to Global Warwatch Network. Controlling a drone deep in hostile territory presents a basic physical problem. Because of the Earth's curvature, standard radio signals can't follow a drone over the horizon. Without a satellite to bounce the signal back down, the operator loses control. Russia solved this by installing Chinese-made Xingkai Tech mesh modems. These allow the drones to talk directly to each other. The modems use frequency hopping to scan for clear airwaves, automatically moving the data link if they detect a jammer. The network is built for attrition. If a relay drone is shot down, the remaining nodes recalculate a new data path in under a second. The control signal just snaps to the next available drone in the web. But there is a massive economic hurdle. A Garand II strike drone costs roughly $70,000. Using those as simple Wi-Fi extenders is a waste of a high-value warhead. The solution is the Gerbera. It's a $10,000 decoy made of plywood and foam. It carries no explosives, just a mesh modem and a camera, acting as a cheap flying router and a missile sponge for Ukrainian defenses. By flooding the sky with these ultra-cheap decoys, Russia creates a robust, expendable communication chain that can sustain itself even under heavy fire. The electronic warfare environment is so intense that Ukraine currently jams more than 50% of all incoming aerial threats. The Garand II fights back with a Kometa antenna that actively filters out jamming signals, paired with a Japanese 6-axis inertial module. This allows the drone to maintain its physical orientation even when its primary navigation is under heavy interference. If the GPS is blocked entirely, the drone switches to computer vision. An onboard processor compares live ground footage with preloaded reconnaissance photos, allowing it to navigate to the target completely offline. This multi-layered approach to navigation makes the latest Garand variants highly resistant to standard electronic suppression. The high bandwidth of the mesh network allows operators to stream live optical camera feeds directly from the drone's nose. This transforms the weapon into an FPV loitering munition. Operators can fly at tree level to hide from radar, hunt for moving targets like convoys, and confirm success in real time. As Ukraine began using interceptor drones and helicopters to take these down, Russian engineers turned the Garand II into an active anti-aircraft platform. These variants now carry rear-facing cameras to spot pursuers, alongside Verba manpads or R-60 air-to-air missiles mounted directly to the airframe. When the operator spots a threat, they trigger a servo to cool the missile's infrared seeker. Once it locks on to the heat signature of the incoming interceptor drone, the onboard missile fires backward automatically. Crucially, the drone still carries its primary 50-kilogram thermobaric warhead. Even after an aerial dogfight, it continues its mission to strike ground targets like this power substation. The Garand II is a multi-role strike and escort platform, capable of defending itself while carrying out long-range kinetic attacks. By 2026, the technical distinctions between a disposable one-way drone and an advanced networked loitering munition have disappeared. Using foreign microelectronics and decentralized swarm logic, Russia has bypassed its lack of a sovereign satellite constellation, achieving deep strike capability through a web of airborne relays. This shift means air defense can no longer just target individual drones. It requires a strategy that can counter an adapting, self-defending network. If you found this breakdown interesting, like the video and share it with someone who follows military tech. Let us know in the comments what you think the next step in drone warfare will be. See you in the next one.